Okay, talking about inferences with means, we said that our means will follow that t distribution. When we don't know the population standard deviation, we're substituting in the sample standard deviation when the conditions are met. So let's talk about what those conditions are. So we need independence, and to check for that, we're going to check for randomization and the 10% condition, which I'll remind you means that our sample size is no more than 10% of the population. And then we need to check that we're dealing with a normal population. We can do that visually by making sure that our display is roughly unimodal and symmetric. If those conditions are met, then I can build a confidence interval by taking our mean from our sample plus or minus the critical value times the standard error. Notice this is the exact same formula that we used for z's, except that our critical value there was a critical z. Now, to look up this critical value, we need both the degrees of freedom and the confidence level because it'll change with both of those. So our degrees of freedom are the n-1, and then we're going to look up the confidence level and either use our calculator or the chart in the textbook. So let's work an example. If n is 15, then my degrees of freedom would be 14, n-1. I want the critical value for a 95% confidence interval. Remember that we said a 95% confidence interval is equivalent to a two-tailed hypothesis test. So half the area on each side. From 95, we have 5% left over. So half of 0.05 is 0.025. So if I'm using the calculator, I would do inverse t, which I find in the distribution menu of the calculator. Inverse t of that 0.025, comma, the degrees of freedom, which is 14, and that's going to give me 2.145. Or on our chart, which is on page A94, so let's go there and take a look at it because I already have it pulled up. On page A94, two-tailed probability 0.05 right here, and then the degrees of freedom 14 here. Look at the intersection of the two. There's our 2.145, exactly as we found with the calculator. Now, let's build a confidence interval. So, first of all, provide a 99% confidence interval for the salaries of airline pilots if a random sample of 12 pilots had a mean of and standard deviation of. Okay. So first of all, it says it's random, so that condition's met. 12 is certainly less than 10% of all pilots, and then we're going to have to assume that this follows a normal distribution. Now, once we do that, we need a 99% confidence interval, so that means 99 from 100 leaves 1%, so 0.01 two-tailed. Let's go look that up on the chart. 0.01 two-tailed. Our degrees of freedom is 11, the 12 pilots minus 1, so 3.106. So 3.106 is our critical T. All right, so our margin of error is that critical T value at 11 times the standard error of the sampling distribution. So that's 3.106 times our standard deviation, which is 17,747, over the square root of the sample size. So if I plug all that in, I'm going to get about 15,933 when I round. So now to construct our confidence interval, we're going to go 97,334 our mean plus or minus that margin of error, 15,933. So that works out to be, if I take 97 minus the 15, that's going to be 81423. And then 97 plus the 15 is going to be 113245. All right, so we would say we are 99% confident that the mean salary for airline pilots falls between 81,423 and 113,245. Okay, that is building a confidence interval. We're going to look more at hypothesis and tests and stuff in the next video.